Okay, guys, we just keep cranking them out, I guess. Another review, more review. Essentially, basically what we're doing is redoing the class in a bunch of hour sections and just taking the highlights, I guess. What we want to do right now is look at the solid state materials, the magnetic properties of materials in a solid state. You know what solid state means? That means it's not fluid. We're not talking about plasmas, liquids, or gases. So a solid material. We want to know the magnetic properties. Well, first, let's look at what we're dealing with, because we're dealing with E and M, right? E is the electricity part of it, and then M, so E and M, is the magnetic property part of it. And that is, that whole thing is two ways of looking at the same thing. So we're going to look at it from the point of view of electric charge first, and then we'll look at the magnetic effects secondly. So let's say we've got a block of some material. There's an Avogadro's number of atoms in it, which means there's an Avogadro's number of positive charges and negative charges. But those positive and negative charges, there's an equal amount. So on the whole, when we do what the electric field is at the point of this Q, this test charge, it doesn't see anything. It sees no charges, even though there's an Avogadro's number of charges over there. Okay? And the whole point is a block of that material has zero charge, and it's because they're all blocking or screening out. We call this charge screening. Okay, they're all screening out the charges from each other, so that if you were to go and look at the net charge, it would be zero. So we call that electric charge screening. Well, for magnetism, the charges are not really charges, so we don't have charges. The dipole isn't truly a dipole. It's a current flowing, right? So we've got this current flowing, and, not caring about the area for a second, but it's a loop, all right? And each of the atoms have the electrons flowing around in a loop. Well, there's a mu for each atom or molecule, and they tend to align with each other. They want to go, they've got a north side and a south side, and they want to kind of align north to south, right? So here's one and here's the next, and they kind of want to do this thing where they start to aligning, right? North to south. So on aggregate, you'll have domains of magnetic polarity, and the domains, kind of like Europe, there's all these little domains where they all do a little bit something different, right? Just a little bit something different. They're lined up a little bit differently. And they do this randomly. So on average, over the whole thing, we have a net zero polarity. And then, of course, table 12.1 has some values for different atoms, magnetic moment atoms, the magnetic moments. But we can do things because of the materials. Different materials are going to have different reactions. So what kind of materials do we have? We've got paramagnetic, we've got diamagnetic, and lastly, ferromagnetic. Okay, so those are the three types, and some of them will be able to be charged up and actually have very large domains, and we could apply a uniform field to the whole thing and get all of those domains to go in the same direction. That would be a ferromagnetic. So in the end, we could have all the domains lined up such that we have a north pole and a south pole, and all the domains are lined up together in one way. Diamagnetic, be a substance like bismuth or whatever, but they don't have each atom, their mu is 0. So that is, they kind of oppose it. Paramagnetic substances will have a net magnetic dipole moment that will align. So these anti-align with applied B field. Let's put a little applied here. But paramagnetics, they will align. So, and they do actually have a magnetic moment. So their magnetic moment is not equal to 0, and they align with an applied B field. So paramagnetics will align, diamagnetics anti-align, and the ferromagnetics really, really, really align. They really want to align. And then not only do they align, they don't go back to random. Once that applied B field is removed, paramagnetics will quickly go back to a random distribution. Diamagnetics quickly go back to a random distribution. But ferromagnetics maintain their aggregate net polarity. Okay. They mention thermal, but we don't deal with it. Okay, so that's what we need to know. Ooh, that's what we need to know for all of paramagnetic, diamagnetic, and ferromagnetic, and electric screening. Okay, so we learned a little bit about electric screening there as well. Okay, so All right, so there's this thing called magnetic susceptibility. Magnetic susceptibility, and we give that a chi. CHI is the term for that. And adding two B fields together, so we'll have a B field that we apply, and we'll have the B field for the magneton or whatever will give us a net B field. It could also be what we call the resultant. Okay, so this is just our B. In the end, our net B. Okay, B field. It's the addition of the material and our applied. Let's say we want to do an applied in a uniform way. What's a good way to do a uniform application? Well, we would have a solenoid. So this is the B field from the solenoid. This is our material on the inside. And this is our net. Okay, so we're adding them together. So we are inserting into our solenoid a material inside the solenoid. We can fill in our material. And so we've got a solenoid going around, wrapped around this material. Just like we put the bar magnet, or I'm sorry, not the bar magnet, the iron inside the solenoid when we did our lab. Okay, it's the same thing. So we have this magnetic susceptibility chi. Well, it turns out that our magnetic field in the material is chi times our magnetic field that we applied from the solenoid. And the book writes it as B0 for the solenoid. So if we were to look at our net B, we're going to use that same equation for net B. Now we've got our B0 plus chi times B0, which gives us our B0 times 1 plus chi. So that is our susceptibility to the magnetic fields. Essentially what we're doing is by adding, this is net, by adding some material inside the solenoid, we are increasing, right? The B field that we would have normally had, we're increasing it, 1 plus chi. So whatever chi is adds to 1 and multiplies by our B field to give us this B net. So we are getting a stronger B field by putting a material on the inside of the B field. And that's our magnetic susceptibility that's allowing us to do that. Yeah, there's a permeability that goes along with this. and I'm not going to write it out because it's confusing with the magnetic dipole moment. The two mu's are confusing, so let's just leave it with this. So I don't know, it's just not as confusing this way. So diamagnetic materials oppose the applied B field and therefore reduce the net B by chi. So a diamagnetic the B net is reduced. So the same equation holds, but we're doing it like this. If it's reduced, then that forces in a diamagnetic material chi to be less than 0. Has to be negative, okay? So diamagnetic chi is less than 0. Paramagnetic chi is greater than 0. And ferromagnetic as well. Okay. Okay. So we talked about the domains and the domain holding, the fact that ferromagnetic all the domains will align up with the external B field, and they'll stay that way. They permanently stay that way, and that's what you call it a permanent magnet. Doing that. So let's talk a little bit about hysteresis. So hysteresis. Hysteresis, I think I got that right. At any rate, it all depends on where you start. Okay, so let's just draw a little. So here's our applied B field. Okay, this is negative of the applied B field. And this would be our B for the material, the resultant, which is the applied 1 plus chi. So it depends on, so hysteresis just means history, right? So it depends on where you start. So if you were to start here and you were to apply some B field, you end up here, and then you apply a negative B field to that. Well, you're at a different spot where you started. So, and you end up with something, say, over here. And then you do it again, and you end up with this point. Okay, so it all depends on where you start. And then where you start has something to do with where you're going to end. Okay? So this is what we call by hysteresis. And you eventually can degauss this material because we're dealing with a ferromagnetic. Okay, so ferromagnetic. We've got some ferromagnetic. We've done all of this charging, discharging, forwards, backwards, all these things. What are we left with in the end? Well, the only time that the ferromagnetic, is at the very beginning, the ferromagnetic was at the origin. It had no net magnetic field coming out of it. That's the only time. So how do you get something degaussed such that it doesn't have a magnetic field in any direction? Well, you can put it in a degausser. There are degaussers that will do that. However, all they are doing is applying a magnetic field over and over, so that, and smaller and smaller and smaller, so that in the end you have this negative thing. But we all know that the field in the other direction is not touched. So if there was a net in the other direction and we had these shrunk, so these go all the way down to 0, so we end up shrinking these down to 0. We still have these, right? Those are still going, and you got to take your object and twist it 90 degrees in the degausser and do it again, and then twist it 90 degrees again and do it again, to actually start to degauss something properly. So one way to degauss is just put in there are things called degaussers. So put it in a degausser, or melt it down. Just melt it down. Cool it off, let it reform, and reform, right? So you melt it down and reform it, and you do that reformation in a zero magnetic field situation. B external is 0. Well, when that reforms, I'm going to guarantee your domains are going to be quite small. You're not going to have domains again. So that's one way to get rid of your ferromagnetic permanent magnetism. So, okay. Degauss that sucker. Melt it down. That's like dropping a nuclear bomb on the situation. Okay. All right, so let's get after this a little bit. We talked about magnetic flux a lot. I'm going to do it again. Here's some area A. We've got a field going through that area A. This is our B field. So our magnetic flux is the B field dot the A. Okay, so our A, I don't know, maybe it has a little bit different N than you would think. So then there's this angle. There's an angle between, and that angle is theta. So it's technically our magnetic is be a cosine of the angle between them. Nice, so that's our magnetic flux. Our change in magnetic flux with respect to time can then be calculated, and that would be either a change in the B field, because maybe the B field is a function of t, maybe the area is a function of t, or maybe it's rotating. This area is rotating, or the B field is rotating, and the area is staying still, but it doesn't matter. But any of these three things can cause a change in magnetic field, and it turns out that our EMF, we can get an EMF by a changing magnetic field. So we have this equation from Faraday. So this is Faraday's law, and it's just straight up Faraday's law. And what it is a statement of is our magnetic flux is equal to some surface I'm actually doing this equation now, not Faraday's law. This is over a surface. And we've got b dot n hat a, and we're doing the integral of that. Okay, not infinity, just a phi, just a capital Phi. So that's how we figure out phi. We've got our flux, and if we want to take Faraday's law and we have n loops, so we're going to make n amount of loops, then we've got n times our d phi dt. All right, so Faraday's law with n loops. I'm not gonna do that. Okay, so this leads us to Lenz's law. And Lenz's law talks about, essentially, what is Lenz's law? It's this. And what is Faraday? What are we getting from Faraday? We're getting an induced EMF. Okay, so Lenz's law is that negative sign. What does that mean? That means that the current from the EMF that is induced is going to be such that the B that it induces opposes the change in the B in the first place. So it sounds like gobbledygook, right? But it's really a real thing. So let's draw ourselves an area. Let's say we've got a B field. Our B field is, let's say that it's increasing. Okay, straight up, the B field is increasing. There's no other things happening. A is not moving, A doesn't change. We're just going to change and make the B field increasing. So our phi increasing with time. So our d phi dt is greater than 0. Okay, because we're increasing. So our we've got a current that's being induced then because of the EMF that's induced. So we have this induced current. And that induced current is such that it wants to make the B that's increasing, it wants to fight it. It wants to oppose it. So which direction is that going to go? In order for it to fight it, you put your thumb along the eye. So you put your thumb along the eye. If let's see, if we put my thumb along the eye, that is the wrong direction. Okay. I'm trying to give you guys a sense of the normal for, this is the normal hat for the area. Okay, so that is the wrong direction. So what direction do we need it to go? We need it to go up on this side so that the B field that is produced, I'm going to just draw a little B field here. This is our induced B. B induced, okay? It has to oppose that increasing B, okay? So this is our induced. We're going to come down on this side. We're going to go up on the other, on this close to us side, we're going up. On the far away side, we're going down. And that is going to induce, or that current has been induced. And it's doing it in such that it's opposing the increasing B field. Okay, so induced has to be less, or it's sucking it away. Fighting it, opposes, okay? It opposes it. So in order to oppose it, that's the only way to do it. You say, oh, well, which direction does my current have to flow so that it opposes it? And then you do your current in that direction, okay? So if at first you've drawn it wrong, then you redraw it and do it right. There are a lot of ways to use Faraday's law. So let's look at those different ways. No, I already talked about it. It's the three ways. Which things can be changed? The B can be changed. The A could be changing. In fact, all of these things could be changing, right? Your change in magnetic flux could come from all three at one time. I wouldn't do that. I would either do 1, 2, or 3. But those are the three things that could happen. And so then we can talk about emotional, not emotional, motional. So motional EMF induced, it comes from these two. Okay, so either the A is physically changing and getting larger, or it's rotating and something's happening with rotations in our theta. Okay, so those two could be happening. So our B stays constant and things happen. Okay, then we get induced current. So what was a good example that we did for this? Let's say we have B field region, and we've got a loop. We'll put a square, here's our B field region. And we'll put a square loop, and our square loop is going into the B field with a certain velocity v, and it's going all the way through, and it's going to come out the other side. So the area inside versus the area outside is changing, right? It's gradually getting bigger and bigger and bigger, and it's doing so as the velocity goes through. And so our EMF is our B field. We've got some height h times height h, and our velocity v. I'm not deriving this. That is what you get. Now, in order for it to happen, here we're obviously increasing. Our phi is increasing with time. So if it's increasing, then that means the current that gets generated wants to be a decrease in current, or I'm sorry, fight that B field. Well, if it's fighting the B field, that means it wants to produce a B field that is in this direction. How does this guy produce a B field here in this direction? Well, it does its current like this. So the current has to flow around the loop like this, okay, on that side. When it's going on this side, it's going to do its current in the opposite direction. Its current needs to go like this. So that is the induced current from motion, okay? And that's all we have to say about that. Set timer for 15 minutes. Okay. We've got the same thing that could be happening from rotations, and our rotation is happening. So we've got some B field, we've got a loop. The loop has some A. We could have many loops. I'm only going to deal with just one loop at a time, but we've got some B field going here. That's our B field, and we'll do one more. Okay, so what are we gonna do? Let's do it like this. All right. Equals minus d phi dt, and this is phi m, of course. What is phi m? Well, let's write it out. Phi m is equal to our b a cosine of theta. But now we're going to spin this sucker. Okay, so our theta, our cosine of theta is going to change. It's going to be moving around. Theta is now a function of t, okay, or we could call it straight up omega t. Okay, so phi m equals b a cosine omega t. And nothing else changes, okay, in time. So if nothing else is changing in time, then our d phi dt, all of that b a, all of those stay, and then we're left with the cosine of omega t, the derivative of that. And that gives us negative b a sine of omega t. And we want negative a negative. So in the end, our EMF is equal to BA sine omega t. Oh, I dropped the omega. I dropped the omega. We need an omega here. There's our omega. And then this bit right there is our maximum. Okay. So we can then write our EMF is equal to max times sine of omega t. And all because we did these things. So if we have an EMF, we have an E field. So EMF implies E field. Okay? And this is yet another thing that Maxwell was working with to get his Maxwell's equations and make sure that everything was copacetic. So our EMF is equal to the closed integral on a loop of our E field dot dl. Okay? So that comes from the fact that our magnitude of our E field is equal to del of our voltage, but I'm not going to put voltage, I'm going to put EMF, okay? So the del of our EMF, but the way we've always seen it is del V, okay, our voltage gives us our E field. Well, this is just the inverse equation to that, okay? And we could say this is equal to our voltage, but this is induced, okay? Induced. So that is for induced current. So we can then say the last and final thing is that our and this is the common Faraday version, okay? Because we had written Faraday's law there, but the common way that we see it is like this. So Faraday's law. So many applications for this. Oh my God. So many. Again, with that, eddy currents develop just from the kinetic energy going through the system and induction and all of that. And so we have kinetic energy of a plate. Let's put a B field down. We've got some region. I'm not going to draw the ones in the middle so that we can slide a plate through. And on the edges of our B field, we can drop a plate and we're going to swing it through with the velocity in this direction. It'll swing through, so it's on a pendulum, it's got some pendulum, and it's going to swing through and go in one side and come out the other. But the velocities, we're going to see, because it's doing this, it's going to lose energy, right? So V2 is going to be less than V1. And the reason for that is kinetic energy initially, or in position 1, is greater than the kinetic energy in position 2. And it's all solely due to the eddy currents that are going to get produced because of Lenz's law, and it's going to produce a current that on this side the current ends up being like this, on this side the current ends up being like this, and those are eddy currents. Okay, eddy currents. So delta KE is not equal to 0. And you can say delta KE is KE2 minus KE1, and that ends up being negative or less than 0. Less than 0. Yeah, but you guys can know how to assign Lenz's law. You can do that. You guys need to be able to do those things. So all metals do this, and that's how we separate out metals in trash cans. Okay, all metals, because they're all conducting materials. So all metals will do that. Okay, so then we get back EMF. Back EMF, and that's when we drive a motor with an EMF and Lenz's law wants to oppose it. So we have a motor, we have a battery, EMF, and Lenz's law wants to oppose the current flow, the current flow wants to oppose whatever magnet we've got going on, and therefore will do a flow that goes in the opposite direction, and that is, so it wants to oppose the magnetic flux change. The change in magnetic flux generating a current or an opposing current and that opposing current then of course only moves about because there is an opposing EMF. That EMF is back EMF. So it happens with a motor. We've got a driving EMF or battery, and then Lenz's law wants to oppose that, and that leaves us with a back EMF. All right, so only happens with the motor. Okay, so excellent job. I think what we're gonna do is we're going to stop here and we're going to continue on with part 7. Oh my God. Okay, so part 7 coming up.